All right, in this lecture, we're going to see a particularly nice technique for solving first-order linear differential equations. So let's recall what those look like. So linear being that the dependent variable and its derivative are both raised to the first power, and their coefficients consist only of the x variable, the independent variable. Or in fact, they could just be constants. And the right-hand side, again, only has the independent variable or is constant. So we're going to see a method for solving these things. But first, we want to write these in a slightly different form, which is called standard form, and it's more useful for our purposes. So let's divide everything by a1. And that would give us dy dx plus, we'll call it p of x. This is really a0 divided by a1 here. And we'll call the right-hand side f of x. And this is called standard form of a first-order linear differential equation. Okay, and before we go on, I want to acknowledge that a linear differential equation may or may not be also separable. So, for example, we have this guy here. This equation is both linear and separable. In fact, you may recall this as the very first differential equation that we worked with in this course. However, this linear equation here is not separable. So some linear equations are separable, some aren't. Of course, when you have an equation that's both linear and separable, then you have the choice of solving it as a separable differential equation using the techniques from 2.2, or you can solve it using the techniques from this section. Okay, so what exactly is the method for solving a first-order linear differential equation? Well, let's look at one in standard form. And the method we're going to use involves noting that the left-hand side of this differential equation is almost, but not quite yet, in the form of the product rule having been applied to the derivative of some particular expression, right? We know the product rule, when used, generates two terms, right? The derivative of the first times the second plus the first times the derivative of the second. And we have two terms, and one of them has the derivative of y, and the other one has y without its derivative. So what we kind of want is we want to have next to y here the derivative of a thing, and the non-derivative of the thing to be next to dy dx, so we can call the whole left side a product rule. So what we need to introduce to make that work is something called an integrating factor. So we're going to let mu be equal to e to the antiderivative of the px. And this is called an integrating factor. So why do we do that? Well, let's notice that the derivative of mu with respect to x is equal to, well, the derivative of e to the stuff is e to the stuff, but then multiplied by the derivative of the stuff, and that would just be p of x, which means that the derivative of mu with respect to x is equal to mu of x times p of x. So now we're going to multiply both sides of the differential equation by the integrating factor, which is mu. Okay, so what we get is mu of x times dy dx plus mu of x times p of x times y is equal to mu of x times f of x. Okay, super cool. Why did we do that? Well, because mu of x times p of x is d mu dx. So we have mu times dy dx, and we're writing the mu without the of x part because we don't really need it, plus that part there, which is d mu dx times y is equal to mu times f of x. Aha, and look at this. That is the derivative of mu times y. That is exactly the form of the product rule here. So the left-hand side becomes the derivative of mu times y. Okay, well then we can integrate both sides and say that mu times y is equal to the antiderivative of mu f of x dx. And that's how we solve this differential equation, because now we can obtain our y. All right, so in practice, what are the steps that we take? Well, clearly the product rule is the theory that underlies this technique, but we don't need to worry about that as long as we just understand that's where it comes from. The actual method is pretty straightforward. So let's see the steps. All right, first write it in standard form. So one of the keys to standard form is that the coefficient in front of the derivative is 1. Okay, if it's not 1, then divide everything by that coefficient. Next is determine the integrating factor, which is mu. And mu is given as e to an antiderivative. Any antiderivative will work of p of x. And now we can just jump straight to almost the solution. Mu times y is equal to the antiderivative of mu times the right-hand side f of x. All right, it's a pretty straightforward process. So let's take a look at some examples. All right, so here we have an example, and I hope you can see that indeed this guy's linear. So the first thing we should do is write it in standard form. And to do that, we're going to divide everything by the coefficient of dy dx, which is, of course, x. Okay, so now the coefficient of dy dx is 1. We can see this is in standard form. So 1 over x is our p of x, and 3 over x would be, of course, our f of x here. All right, so the next thing we should do is find the integrating factor. So we're going to construct mu by taking e raised to the antiderivative of p of x. Okay, well that's not too bad. So this is e to the ln of absolute value of x. And here you may be wondering, and this of course becomes the absolute value of x. However, we don't even need the absolute values here. Why don't we just define our mu to be positive x? And there may be a couple questions emerging right here. One is, why don't we need the absolute values here? And the other is, why didn't we add a constant when we integrated? And actually, I'm going to answer the constant one first, because the answer to that will help us understand why we don't need the absolute value. So let's just pull this down for a moment, and let's suppose we did put a constant in there. So, all right, well, that's e to the ln of absolute value of x times e to the c. So if you recall, when we were constructing this process, we took the integrating factor and multiplied both sides of the differential equation by it in order to reverse engineer the product rule. Now, if we included the constant here, then in the background, we would be multiplying both sides of this differential equation by e to the c. And that's completely unnecessary. You could just cancel e to the c out and then proceed. So the constant's utterly unnecessary. So what about the absolute value? Why can we throw that away here? Well, for virtually the same reason. Absolute value of x really means this. So when you're multiplying both sides of an equation by the absolute value of x, you're either multiplying it by x or negative x. But again, if you're just multiplying everything by negative x, you can cancel all the negatives out. You might as well just multiply by positive x. So it's completely unnecessary to have the absolute value there. So in that case, we're just going to let mu equal x. And now we can skip to the form of our answer. So we get mu times y is equal to the antiderivative of mu times f of x dx. So in this case, that would be x times y is equal to the antiderivative of x times our f of x, which was 3 over x. So x times y is equal to the antiderivative of 3. And of course, we get 3x plus a constant. We'll call it c1 for now. And finally, solve for y. And there's our general solution. All right, it's our general solution. And we can write down an interval of definition. Those are two pretty good ones right there. Okay, so we have finished that problem, but I want to just make a new definition based on the solution that we worked out. So in a general solution, if a term approaches 0 as x, or the independent variable, approaches infinity, that term is called transient. Okay, and they have a name because they have a role. And that role is actually that they become unimportant, meaning they don't affect the long-term behavior of the solution. So for example, in the solution y equal 3 plus c over x, which we just obtained, c over x is a transient term. Okay, which means that as x approaches infinity, c over x approaches 0. So the long-term behavior of the entire family of solutions is the horizontal asymptote y equals 3. Sometimes an entire solution can be transient. You might have something like y equals c ln x over x. As x approaches infinity, ln x over x does approach 0. You can establish that, of course, with L'Hopital's rule, which means that the long-term behavior of this family of solutions is the asymptote y equals 0. All right, so first thing we should do is write it in standard form. And we'll do that by dividing everything by cosine squared times sine. Okay, we can clean this up a little bit. We have dy dx plus, well, let's see, we have cosine over sine, so that would be cotangent of x times y. And on the right, we have secant squared of x times cosecant. Okay, so this is now in standard form. So let's find our integrating factor. So we know mu is going to be e to the antiderivative of p of x, which is the coefficient of y. So that's e to the antiderivative of cotangent of x dx. And perhaps you know or recall that the antiderivative of cotangent is natural log of sine. But if you don't, and this is going to happen sometimes where it's just a complicated integral in there, then we'll have to lift it out and work it out as side work. Okay, well that's cosine of x over sine of x. And we can do a u substitution. So we get du over u, which is ln of absolute value of u, which is ln of absolute value of sine of x. And so therefore, our mu, which is e to the antiderivative of cotangent of x, is e to the ln of absolute value of sine of x. So we can just let mu be sine of x. Okay, so we arrive at this form. Mu times y is equal to the antiderivative of mu times what was on the right. And this is the standard form of the differential equation that we left off with. So what do we have? Mu, which is sine of x, multiplied by y is equal to antiderivative of mu, which is sine of x, times f, which is the right-hand side there. Secant squared of x, cosecant of x, dx. Well, it's convenient that sine and cosecant cancel. So we have sine x multiplied by y is equal to antiderivative of secant squared x dx, which is, of course, tangent. So sine of x times y is tangent of x plus a constant. And now we'll divide everything by sine of x. Tangent divided by sine is secant, of course, plus cosecant over here. And since this is our final answer, let's just call our constant c. Okay, this has no transient terms. And let's try to find some intervals of definition here. Okay, well, secant is undefined at odd multiples of pi over 2, isn't it? And, well, cosecant is undefined at even multiples of pi over 2, namely 0, pi, 2 pi, 3 pi, etc., which means that our general solution is undefined at any multiple of pi over 2. Okay, so sample intervals of definition. Well, how about 0 to pi over 2? Or like 5 pi over 2 to 6 pi over 2, etc. If there were an initial value given in this problem, then we'd have to go with the interval of definition that included the x-coordinate of the initial value. Okay, first things first, let's write in standard form. So that's just a matter of dividing everything by x.
It's a standard form.
Very good. So now let's determine our mu, the integrating factor. So mu will be e raised to the integral of p of x, right? The stuff that's right, the coefficient of y here. So let's write that as 5 minus 1 over x. And we can see that's e to the 5x minus ln of absolute x, which is like e to the 5x over e to the ln of absolute x. And so we can just set our mu to be e to the 5x over x. Great. So now we can jump to the form here, which is mu times y is equal to the integral of mu times f of x dx. So that would be e to the 5x over x times y is equal to the antiderivative of e to the 5x over x times f of x, which was 2x squared, and dx. So we just need to work out this integral. All right, well, let's lift it out of the problem. We have 2x e to the 5x dx. So we are evaluating this as side work. And hopefully you're looking at that and one thing comes to mind, which is integration by parts. So let's do that. So remember, with integration by parts, there's a mnemonic Lie8 for assigning the variable u. So L stands for logarithms, I is inverse trig, A is algebraic stuff, T is trig, and E is exponential stuff. And so you look at your integrand and look for logarithms first. Don't see any. Look for any inverse trigs. We don't see any. Look for algebraic stuff. And yes, we have 2x, so that should be our u. So for integration by parts, we will let u be 2x. So our du is 2dx, and our dv is what we did not choose for u, so that would be e to the 5x dx. And so our v will be the antiderivative of that, which is 1/5 e to the 5x. And so our integral is this thing, ultraviolet voodoo. U times v is 1/5, it's 2/5 x e to the 5x minus v du, which would be 2/5 e to the 5x dx. And we can integrate that by just saying that's 2 over 25 e to the 5x plus our constant. And that's the end of the side work. So therefore, pasting in our form, we have e to the 5x over x times y is equal to 2/5 x e to the 5x minus 2 over 25 e to the 5x plus a constant. And we will just multiply everything by x and divide everything by e to the 5x to isolate y. So we get y is equal to 2/5 x squared minus 2 over 25x plus c1x e to the negative 5x. And that's our general solution. This term here is transient. As x approaches infinity, that term does approach 0. Again, you can establish that using L'Hopital's rule. All right, well, what about the interval of definition? Well, the domain of this function is all real numbers. And this function is differentiable on its entire domain too. So you would be forgiven for putting forth negative infinity to positive infinity as an interval of definition. But this is a case where that's actually not true. That's not the interval of definition here.
You're kidding.
There's a point we need to exclude, or else this entire process isn't going to work. And that would be x equals 0. Our first clue was right here, 5x minus 1 over x. X is not allowed to be 0 for that term to exist. That fact manifested over here as well. Can't take the natural log of 0. Can't have 0 there. So we need to exclude 0. In this case, 0 is referred to as a singular point. It's distinct from a singular solution, which we saw in the last section. So what would be some intervals of definition then? Well, the function has a domain of all real numbers, but we have to exclude 0, so negative infinity to 0 would be good. 0 to infinity would be better. Well, just because I like the positives, but it's really the same. And there we are. All right, here we have an initial value problem. And this one's actually the model that we obtained when we looked at Newton's law of cooling in section 1.3. So where capital T was the temperature of a body, and Newton's law of cooling says that the rate of change of the temperature of a body is proportional to the difference in temperature of that body with the surrounding medium's temperature, which is Tm. So we're actually going to solve this differential equation because it's linear. And it's an initial value problem. We're told that the initial temperature of the body at time 0 is equal to T0. So what makes this kind of neat is there are no actual numbers. We're going to get a solution in terms of T0 and Tm and K, and those will be determined by the specific situation that we're dealing with, the initial temperature of the coffee cup or the ambient temperature. So first let's get this thing into standard form. Okay, so dt is equal to k times t minus k times tm, and we will move the k times t over. So we have dt minus k times t is equal to negative ktm. All right, this is now in standard form. So let's now find mu, the integrating factor. So we know that mu is equal to e to the antiderivative of the coefficient of t in this case. So that'll be negative k dt. So mu will be e to the negative kt. And so the form of our solution we know is mu times capital T is the antiderivative of mu times the right-hand side. So mu being e to the negative kt times t is the antiderivative of e to the negative kt times f of t, which was just the constant negative ktm. So we have e to the negative kt times capital T is equal to, we can factor this constant out, and so we're just integrating e to the negative kt dt. And the antiderivative of e to the stuff is e to the stuff, but we know to divide by negative k because there's a u substitution in here. And we'll throw our constant in, call it C1. Okay, so this cleans up a little bit. Those negative k's cancel. So we have e to the negative kt times capital T is equal to Tm times e to the negative kt plus our constant. Very good. Let's multiply both sides by e to the kt. So we get T is equal to T little m plus C1 e to the kt. And since this would be our general solution, we can just call that constant c. All right, now remember, when we first talked about Newton's law of cooling, we established that no matter the situation, k had to be negative. So if we know that k is a negative constant, then this term right here is actually a transient term. And that makes sense because as t approaches infinity, we want that term to go away so that the actual temperature of the body approaches simply the ambient temperature, the temperature of the surrounding medium, Tm. Okay, now this was an initial value problem, so now we're going to plug in the initial value. The initial value was that t of 0 is equal to t0. Okay, again, this is a very general model here, so we're leaving it up to the actual scientists using it to plug in these specific parameters. So this means that capital T is t0 when little t is equal to 0. Okay, well, e to the k times 0 is just e to the 0, which is 1. So t sub 0 is equal to t sub m plus c. And so solving for c, we can see that c is t sub 0 minus t sub m. So the particular solution is the general solution here, but with little c replaced by t0 minus tm. So that would be tm plus what used to be a c is now that, e to the kt. And that's our final answer. So how does this get used? Well, suppose that you have some initial body which is 300 degrees and a surrounding medium which is 70 degrees. Then this would be your model for the cooling of that body. 300 minus 70 is 230. E to the kt. Now you'd still need to figure out what little k is, which depends, of course, on the substance of the body that's involved and how much of it is exposed to the ambient space, depending on its geometry, what it's made out of, etc. But this would be the model describing the temperature of that object at time t.